Today we are going to discuss about vestigial sideband modulation technique. In our previous class we discussed about single sideband modulation technique, and we know in that single sideband modulation technique one of the sideband is suppressed and we will transmit only the other sideband to the receiver side. Then the main limitation associated with single sideband is the practical difficulty in suppressing the unwanted sideband frequency component. And it was observed in practice that such a process results in eliminating even some portion of the wanted sideband. And this is because the message has information starting from zero frequency and spreads up to a maximum of FM hertz. And in such scenario, the first wanted and unwanted frequency components lies very close to each other at the carrier frequency Fc. So an attempt to attenuate unwanted component will in turn leads to attenuation of wanted component. Let's try to understand this with the help of frequency spectrum of DSB-SC wave. We know this is the frequency spectrum of DSB-SC wave. Then to obtain single sideband wave, we need to suppress one of the sidebands. And when we consider the upper sideband, it is from Fc to Fc plus Fm, and the lower sideband is from Fc to Fc minus Fm. So if we want to remove one sideband, then we need to cut precisely at the Fc frequency. Okay, then we will remove either Fc to Fc minus Fm frequency for the transmission of upper sideband, or we will remove Fc to Fc plus Fm frequency for the transmission of lower sideband. So for that, the precise cutting at the Fc frequency is mandatory. If that slightly deviate from Fc frequency, then that will eliminate some portion of the wanted sideband. Because in many cases the message has information starting from zero frequency and spreads up to a maximum of FM hertz. So that lower frequency components of our information signal lies very closer to Fc frequency. For example, consider our modulating signal frequency changes from 0 Hz to 10 Hz. Then when we consider the upper sideband, its frequency range will be from Fc to Fc plus 10 Hz. Okay. And when we consider the lower sideband, its frequency range will be from Fc to Fc minus 10 Hz. So when we consider the upper sideband portion, that Fc plus 0.5 Hz or Fc plus 1 Hz frequencies are very close to this Fc frequency. And when we consider the lower sideband, that Fc minus 0.5 Hz frequencies are very closer to this Fc frequency. Then when we try to cut precisely at Fc frequency to remove one sideband, and if that deviates slightly away from that Fc frequency, then that frequencies comes closer to Fc may get removed. So that Fc plus 0.5 Hz frequency or that Fc minus 0.5 Hz frequency may get removed when we try to remove that unwanted sideband from this. So if we try to remove one sideband from this, it may result in eliminating even some portion of the wanted sideband, because in many cases the message has information starting from zero frequency and spreads up to a maximum of FM hertz. So since the first wanted and unwanted frequency components lies very close to each other at the carrier frequency, any attempt to attenuate unwanted component will in turn leads to attenuation of wanted component. Then one way to compensate for this loss is to allow a vestige or trace or fraction of unwanted sideband along with the wanted sideband. And this thought process led to the development of yet another amplitude modulation termed as vestigial sideband suppressed carrier technique or Vsb-SC technique. And this Vsb-SC is more commonly termed as Vsb, vestigial sideband, and the suppressed carrier as implied. Let's now consider the equation for the vestigial sideband wave. To get the equation of vestigial sideband signal, we are starting from the double sideband suppressed carrier signal equation. We have already derived this equation in our part 3 class. You can go through that video class if you have any doubt. So the double sideband suppressed carrier signal is represented as V DSB SC is equal to MVC by 2 cos omega C minus omega m into t minus MVC by 2 cos omega C plus omega m into t. Then if lower sideband is the wanted sideband in the case of vestigial sideband, then the instantaneous voltage of the vestigial sideband may be expressed as Vsb is equal to MVC by 2 cos omega C minus omega m into t plus f of minus MVC by 2 cos omega C plus omega m into t. And here this f represents the fraction. So if lower sideband is our wanted sideband, then we will transmit that lower sideband fully along with a vestige or fraction of the upper sideband. Then alternatively, if upper sideband is wanted sideband, then the instantaneous voltage of vestigial sideband may be given by Vsb is equal to minus MVC by 2 cos omega C plus omega m into t plus fraction of MVC by 2 cos omega C minus omega m into t. So if upper sideband is the wanted sideband, then we will transmit that upper sideband portion completely along with a fraction of the lower sideband. When we consider this vestigial sideband technique, the power and bandwidth requirement in the case of vestigial sideband will be slightly more than single sideband but less than double sideband technique, because here we are transmitting one full sideband plus a portion of the other sideband. So the power and bandwidth requirement will be greater than SSB technique, but it will be less than double sideband suppressed carrier technique. Let's now consider the block diagram representation of vestigial sideband generation by bandpass filtering. The block diagram representation is exactly same as that of single sideband generation case, but here the cutoff frequencies of the bandpass filter will be different. Okay, because in vestigial sideband technique we are transmitting a full sideband and a fraction of the other sideband. So if the cutoff frequencies are Fc minus Fm and Fc plus Fv, where Fv is the vestige component frequency, then the lower sideband and vestige of the upper sideband are chosen for the transmission. Then the equation for the vestigial sideband signal will be Vsb is equal to MVC by 2 cos omega C minus omega m into t plus fraction of minus MVC by 2 cos omega C plus omega m into t. And alternatively, if the cutoff frequencies are Fc minus Fv and Fc plus Fm, then the upper sideband and vestige of the lower sideband are chosen for the transmission. Then the equation for the vestigial sideband wave will be minus MVC by 2 cos omega C plus omega m into t plus fraction of MVC by 2 cos omega C minus omega m into t. So in this vestigial sideband technique, we will transmit either the lower sideband component fully plus the fraction of the upper sideband, or we will transmit the upper sideband component fully plus a fraction of the lower sideband component. And when we consider this case, the fraction of the upper sideband component is from frequency Fc to Fc plus Fv. We know the full upper sideband component is from Fc to Fc plus Fm. But here we are transmitting a fraction of that upper sideband component, and it is from Fc to Fc plus Fv. And when we consider this case, here we are transmitting that upper sideband component completely plus a fraction of the lower sideband component. And when we consider this fraction of the lower sideband component, it is from Fc to Fc minus Fv. The complete lower sideband component is from Fc to Fc minus Fm, but in this case we are transmitting a fraction of that lower sideband component, and that fraction of the lower sideband component is from Fc to Fc minus Fv. So here we will transmit either this one or this one to the receiver side, and from this signal at the receiver side our actual information is extracted. Let's now consider the frequency spectrum of the vestigial sideband wave. We have two frequency spectrum, one for vestigial sideband signal is equal to upper sideband plus vestige of the lower sideband, and the other for vestigial sideband signal is equal to lower sideband plus vestige of the upper sideband. So first consider this one. This is the frequency spectrum for the vestigial sideband signal if we are transmitting that upper sideband component plus a fraction of the lower sideband component. So here we will transmit that upper sideband component fully and we will transmit a fraction of the lower sideband component. Then as we seen in the case of that block diagram case, the vestige of the lower sideband component is from Fc to Fc minus Fv. In the textbook actually this portion is shown at Fc minus Fm, but here I have shown this at Fc minus Fv to get clear idea about that frequency range. Okay, then if we are transmitting the lower sideband plus vestige of the upper sideband, then the frequency spectrum will be like this. So here we are transmitting the lower sideband completely plus vestige of the upper sideband. So that complete lower sideband portion is represented here at Fc minus Fm, and that vestige of the upper sideband is represented here at Fc plus Fv. So here we are transmitting the frequencies from here to here, from this Fc minus Fm to Fc plus Fv, and here we are transmitting the frequencies from Fc minus Fv to Fc plus Fm. And also here we can see that vestige of the sideband component amplitude is less, because here we are transmitting only a fraction of that sideband component, so its amplitude level will not be equal to that full sideband amplitude. Okay, then from this we can calculate the bandwidth required for vestigial sideband, and that bandwidth is equal to, from this one we can write Fc plus Fm minus Fc minus Fv, and from this one we can write Fc plus Fv minus Fc minus Fm, and that is equal to Fm plus Fv. So the bandwidth required for vestigial sideband is the frequency of the modulating signal plus vestige band. Let's now consider the time domain representation of the vestigial sideband wave. We know the modulated wave will have two sine waves. One corresponds to this equation and the other corresponds to this equation. Okay, then if Fv is very close to the other sideband, then its shape will be more like double sideband suppressed carrier wave. Because when Fv is very close to the other sideband, or when Fv is large value, then here that Fc plus Fv will be very close to Fc plus Fm value. So this fraction almost consists of that full upper sideband, and in this case if that Fv is close to the other sideband, or that Fv is very large, then that Fc minus Fv will be very close to that Fc minus Fm value, and this fraction may contain almost all of the lower sideband, and hence these equations may look like double sideband suppressed carrier wave equation, because these fractions are almost equal to that corresponding sidebands. Okay, so if that Fv is very large in this equation, it may contain this lower sideband plus almost full of the upper sideband, and in this equation it may contain this upper sideband plus almost full of the lower sideband. And hence if Fv is very close to the other sideband, or if Fv is very large, then its shape will be more like double sideband suppressed carrier wave, or it will look like this one. Okay, we have already seen this in our part 3 class. You can go through that class if you have any doubt. Then if Fv is significantly lower than the other sideband frequency, then its shape will be like single sideband, because when Fv is very small, then when we consider this fraction, that Fc plus Fv component lies very close to Fc frequency, and here that Fc minus Fv component lies very close to that Fc frequency. So these fractions are very small. Okay, and hence that equations look like the equations in the case of single sideband case. So if Fv is significantly lower than the other sideband frequency, then its shape will be like single sideband, and we have already seen that shape. Here is that one. This is the single sideband wave shape. Okay, and when we are transmitting that upper sideband portion plus vestige of the lower sideband in the vestigial sideband case, and if Fv is very small, then the wave shape will be like this. And if that vestigial signal is equal to lower sideband plus vestige of the upper sideband, and if Fv is very small, then that wave shape will be like this. We have already explained this single sideband wave shapes in our part 4 class. If you have any doubt, you can go through that video class. Let's now consider the power relations in the vestigial sideband wave. We know the vestigial sideband wave consists of one sideband completely and a vestige of the other sideband or a fraction of the other sideband. So the modulated wave contains energy due to these two components. Then we know the total power in the double sideband suppressed carrier modulated wave will be P DSB SC is equal to V LSB square divided by R plus V USB square divided by R, where all the voltages are RMS values and R is the resistance in which the power is dissipated. Then we know P LSB is equal to P USB is equal to Vsb square divided by R, and that is equal to MVC by 2 divided by root 2 all square divided by R, and that is equal to M square Vc square divided by 8R, and that is equal to M square by 4 into Vc square by 2R, and we know this Vc square by 2R is equal to Pc. Then substituting these equations in the total power equation, we have P DSB SC is equal to M square by 4 into Vc square by 2R plus M square by 4 into Vc square by 2R. Or we can write P DSB SC is equal to M square by 4 into Pc plus M square by 4 into Pc. Then when we consider the vestigial sideband wave, if lower sideband is the wanted sideband, then the power in the vestigial sideband wave P Vsb is equal to M square by 4 into Pc plus fraction of M square by 4 into Pc. This M square by 4 into Pc is the power in the lower sideband, and this M square by 4 into Pc is the power in the upper sideband. So here, if LSB is the wanted sideband in vestigial sideband case, then we will consider the power of the lower sideband completely, plus we will consider a fraction of the upper sideband power. Then alternatively, if upper sideband is the wanted sideband in vestigial sideband, then power in Vsb is equal to fraction of the lower sideband power. So fraction of M square by 4 into Pc plus M square by 4 into Pc. So this is the full power of upper sideband and this is the fraction of the lower sideband power. Then from this equation we can see that this equation relates total power in the vestigial sideband modulated wave to the unmodulated carrier power Pc. Then from this we can calculate the maximum power in the vestigial sideband wave. We will get the maximum power when M is equal to 1. So by substituting M equal to 1 in these two equations, we will get that maximum power in vestigial sideband wave is equal to Pc by 4 plus fraction of Pc by 4 when M is equal to 1. Thus we need only a maximum of 25% to 50% of unmodulated carrier power for the transmission of vestigial sideband wave. And this is correct also because in the case of vestigial sideband wave, 1/6 of total power is utilized by one sideband and a fraction of 1/6 for the transmission of the vestige.